Welcome back to section 3-1 in PreCalculus. This is the second half of the lesson talking about the natural base e, which is a number, and also the logistic function. So this idea of natural base, you see this on your calculator with a button ln, because right above the ln button you see e to the x. So ln stands for the French version logarithme naturel, and then e to the x is that inverse idea, just like the other button next to that is log and 10 to the x. So we'll talk about these inverse functions, the log and the natural log, in just a minute. So what you need to know is that e is very close cousins with his friend pi. What does pi represent? Well, it's a sort of non-repeating, non-terminating decimal, and you know it as 3.14, etc., etc. E is a lot like that. Think of when you see e, don't be scared. It's just a new number that we're representing with a letter instead of numbers. But if you use your calculator and say e to the first power, you get the actual decimal approximation of e, just like pi is 3.14, e is 2.718, and that's how I want you to think of it. The official formula for e is a little harder to swallow. We say that e is the limit of this function, 1 plus 1 over x to the x, as x approaches infinity. So the bigger numbers you put in here, so 1 over 1 million, say, 1 plus that will be 1 and 1 millionth to the 1 million power. So that's a really big number, but anyway, what you get is 2.718 as you have these x values approaching infinity. So worry less about that formula for now, because we use that much more accurately and precisely in calculus next year. For right now, think of this letter, the script e, as 2.718. Now, this is also a basic function, f of x equals e to the x, and if you graph that, if we have positive exponents for the x values here, positive or negative, then 2.718 to any of these numbers would give you a graph a lot like f of x equals a times b to the x. So it looks like this. And the magic thing about f of x equals e to the x is that it always crosses through at positive 1. So when x is 0, e to the 0 power is 1. And also it has the limit here, it never crosses the x-axis. As you get bigger and bigger negative numbers for your x exponent, 2.718 to the negative 100 would be the same as, hang on, e to the positive 100 as a denominator. So take your negative exponent, put it in the denominator, or switch numerator and denominator, then it changes that sign. So 1 over 2.718 to the 100th power is a very, very tiny number, because we're multiplying this e, this 2.718, times itself 100 times, and then making that a fraction, 1 over that huge number. So we've got a limit as x approaches negative infinity, the limit is 0. As x approaches positive infinity, going this way, the value is positive infinity. So you remember from the last section that we have the exponential function, which is a times b to the x. And we called a our initial value, and b was the base. And there's x in the exponent, so it is an exponential function. So now this looks surprisingly familiar with our e to the x, but what about the a's and the b's? Well, here's how we can fit an exponential function to be a little more like, a natural base function to be a little more like our exponential function. And here's what it'll look like. So for the exponential function, the full version is A, an initial value, times E, because now we're using E as our base. But I need to be able to sort of tweak these values a little bit better. I could pick any base here and calculate my initial value and then be able to graph it and use whatever x values I needed. But I can't change the E here as my base. The E is always 2.718. So in order to be able to curve fit this beyond just the initial value, I'm putting a K in there. K stands for constant. Well, it doesn't really, but in math class it does. So K is going to be just some other value, and now we have to do some curve fitting, finding an initial value, keeping the base always the same, unlike in our exponential function, and finding a K value that makes it fit to some data. And we can fit these to each other. We really can. So for example, if we were trying to I'm going to do the exploration 2 on the bottom of page 257. It says, step 1, graph f of x equals 2x. Well, what does that look like? And then you're going to graph the e to the x. So f of x will be e to the kx, and we're going to use a couple different values for the k. So in your calculator, it would have to be entered like this. E to the, and then it gives you parentheses, 0.4 x, and then put the parentheses after that. If you don't put, you can leave this ending parentheses off, but if you were to write it like this, you get a straight line, because this is doing order of operations, and it says here's the exponent, and then I take this number and multiply it by x, which is not what you want to do. So 0.4 to the x, there's 1. Oh, sorry, this would actually be y1. So this is y2, y3, e to the 0.5x, and y4 would be e to the 0.6x. And so as you keep going, you see that these graphs are sort of stretched out like this, and then they're getting closer and closer to this graph right here, 2 to the x. So what is the exact value? If you look at 0.7 to the x, I'm sorry, e to the 0.7x, that one, I'll make it blue. That one is actually just barely on the other side of your original line, but quite close. So the final answer is that we need a k value of 0.693 to make e to the kx equal 2 to the x. So that means that if we did 2.718 to the 0.693 power, we get about 2. So continuing on, let's look at one of the examples from page 258. You're given these 3 functions, and you're asked to describe the transformation from the original e to the x, or e to the 1x. Hang on. And so here are the transformations. So let's learn how to decipher this stuff in the exponents, because it's a little bit similar to the polynomial stuff, and I think you'll catch on quickly. So for g to the x, what are we doing to the x before we continue with the function? Ooh, that sounds like it's going to be a horizontal kind of thing. So if we started with e to the x, and now we're doing e to the 2x, that means we're actually doing something on the horizontal scale, and because it's multiplication, not addition or subtraction, then then it is a stretch or shrink. Now, if it's 2 times x, then we have to think of it as the opposite effect. So this is not a horizontal stretch, this is actually a horizontal shrink, which sounds just like all the other analyses that we did in the polynomial chapters. So by a factor of 2. So what does that graph look like? Well, if the original one, let me make the original one blue, then a horizontal shrink by a factor of 2 would sort of close this stuff in a little bit. And we keep the same value here. It'll always cross through y equals 1, because as soon as we pick x as 0, e to the 2 times 0 is still e to the 0, which is still 1. So now this graph would look a lot more like this. Kind of looks like a vertical stretch, doesn't it? But don't get them confused. They actually do graph out differently. So next one, h of x equals e to the negative x. Again, we're doing something to the x before continuing on with the rest of the function. So for h of x equals e to the negative x, this will be a horizontal thing, and with the negative sign you can think of it as a reflection. So what does it mean to start with your original function and reflect it horizontally? Well, it's like putting a mirror here to reflect the left side to the right side, and vice versa. So when you have negative exponents, it makes them reflect this way. And we actually saw that as doing the 1 over e to the positive x and such, and things like that with the bases from the previous section. So horizontal reflection, meaning y-axis reflection when you have negative exponents. Lastly, k of x equals 3 times e to the x. Ooh, finally, we're doing something to the function after we've taken care of that exponent. So if the original one is here, then this 3 out here in front of all of it is actually going to be a vertical effect, and it does obey the logic of 3 times the rest of it, so this is a vertical stretch by a factor of 3. So what does that look like? Well, that's going to be, sorry, there we go. That's going to slide each of these y values up by a factor of 3. So now you get a graph like this. And look at that. E, if we chose e to the 0, meaning right along our x-axis, e to the 0, e to the 0 is 1, 3 times 1 is 3. So now, here's our new y-intercept at 3, whereas our old y-intercept was 1. Sorry, graph not drawn to scale. So here's the last part, the logistic function. It's a lot like the exponential or the natural function, but the idea is that instead of continuing on up to infinity, we have a limit. We have a point where we have to stop growing. And so it's sort of like having 2 horizontal asymptotes. And we will find the locations of those asymptotes very soon. So here's the formula. And this is how we tie in the exponential formula and the natural base. So for logistic functions, this is what the general formulas. There are actually 2. C divided by 1 plus a times b to the x. Ooh, that looks familiar. Or f of x could be equal to c divided by 1 plus a times e to the negative kx. So there's no negative sign here. There is on this one. And the choice here is simply, do you want to use natural base or not? This has a base that can change. This is the natural base, e, which does not change. E is not a variable. It's like 2.718. It's like writing pi right there. So you can use either one, and you will get the same effect of this sort of stretched out S-shaped curve. And the reason that you want to do this, or that you'd want to use one of these functions, is for the idea of Black Friday shopping. When the prices are very low, then they sell quickly. As the prices increase, then you get a limit to how many these people are going to want to buy. So that $10 Nerf gun, yeah, they probably sold a lot of those. But as the prices increased to $20, people weren't really buying them so quickly. Also, this can represent population and decay. So just like we used this function to talk about exponential growth or decay, now we can also use the logistic function to talk about growth and decay. What was it that we used in this function to talk about decay? What did we make positive or negative or fractions or anything? Yep, it was the b value had to be between 0 and, oops, I wrote those the wrong way. The b value was going to be between 0 and 1, and that made it decay. So pretty close to that, we have the same effect that we can use on these logistic functions. So these are now growth, or versions of the growth logistic function, growth. But what about the decay functions? So these are the growth versions. When you want a decay version, then you actually would make the base bigger than 1. So from the starting point of this original exponential function, we had growth when the base was greater than 1, but now, since it's in the denominator, we actually get decay when the base is greater than 1. Also, here, this would be the growth function, or now when we choose a k that's actually negative, meaning e to the negative times negative, so e to the positive k, then it ends up being decay. I'm sorry if that was counterintuitive or confusing, but as you practice these, I think you'll understand better. So k less than 0, that means negative. So if we put a negative and a negative k value in here, we end up with a positive thing, and then it makes it decay because we've got this thing in the denominator. Let's see that in action. Now I'm going to do example 6 on page 259. One of the nice things about these logistic growth functions, or logistic decay, is that they're pretty easy to sketch on a graph. This numerator value will always be the limit to growth. So when you have a growth function and it's going like this, whatever this top horizontal asymptote is, that's actually your C value. So if we are trying to graph these functions, f of x and g of x, and also find the y-intercept and the horizontal asymptotes, then I've got a pretty easy start here because this numerator is going, oops, yes, this numerator is going to be one of those horizontal asymptotes. So here's the graph for f of x. I look at the numerator, I make that one of my y values, and I draw a horizontal asymptote right there. Now, the other horizontal asymptote is actually going to be the x-axis every time, because we can't get negative y values out of growth functions. So we never have negative populations or anything like that. Next, what about some of the y-intercepts and some of the graph look to this? So we'll start with a table of values. Here's my x, here's my f of x. When x is -2, let's start there. Then 0.7 to the -2 power is 2.04. So 3 times 2, that's about 6, plus 1 is 7. 8 divided by 7 is just a little more than 1. So here's my x value of -2, and my y value is right about there. So then, what about here? I've got x is -1, so 0.7 to the -1, that's 1.4. 3 times 1.4 is 4.2, plus 1 is 5.2. 8 divided by 5.2 is 1.53. So this was a little more than 1. So now I'm here at x equals -1, and my y value is 1.53, so I get a little bigger. Then, what am I going to get when x is 0? Well, there's my table of values. When x is 0, what is my y value? So I go in here, 0.7 to the 0 power, that's 1. 3 times 1 is 3, plus 1 is 4. 8 divided by 4 is 2. Continue on. If x is +1, now I've got 0.7 to the +1 power, which is 0.7. 3 times 0.7 is 2.1, plus 1 is 3.1. 8 divided by 3.1 is 2.58. So now I'm up here, and I can continue with this process. 0.7 squared is 0.49, times 3 is 1.47, plus 1, 2.47. 8 divided by that is 3.2, 3, 8, etc. So you can see that this graph is stretching up like this, and eventually it's going to turn and come close to that upper boundary. So what was the y-intercept? Y-intercept is when x is 0. So that's y equals 2. And the horizontal asymptotes are the x-axis, which is y equals 0, and y equals 8. How about this one? Well, we can sketch that graph pretty quickly by saying the numerator is the limit to the growth, so there's 20. My horizontal axis is another horizontal asymptote, and now we've got the base of e. So if I make a table of values, here's my table, I can sketch this graph. I have a y-intercept here when x is 0, so that y-intercept happens at 6.666, which would of course be equal to 6 2/3. There we go. So there's my y-intercept, and that means I'm going to come up like this, cut through that, and come up close to my limit, my upper horizontal asymptote of 20. And that happens pretty quickly. You can see that when x is 1, I'm already at 18. When x is 2, I'm already at 19.9. When x is 3, I'm really close to that upper limit of 20. So that's how you would graph these and sketch them, and we'll find these this point here called the point of inflection in just a minute. So when we talk about population models, we can have exponential growth models, which they say San Jose, California would be an exponential growth model, which means there's no limit. Or we could have a logistic population model, which means there is an upper limit. Maybe they run out of space. Probably they'll run out of water first. And I'm going to call this upper limit. So that would be the Dallas example. Now, you won't have to find out what these equations are, you'll just have to be able to use them. So here's the tricky thing to get used to using population models. You'll see them start off with when t is the number of years since whatever. So maybe this is year 2000, or maybe it's years since 1900. They use 1900 for Dallas and 2000 for San Jose. And you see that t is the new variable where you saw x and all of these other things. So let me do the Dallas population one. So they say p of t, meaning population as a function of time, is 1,301,642 divided by 1 plus 21.602 e to the negative 0.05054 t. So big long equation, lots of numbers, but we can sort of look at this and understand that when t is the number of years since 1900, then we can make a table of values and realize that the upper limit to the growth is 1.3 million. So it's going to do something like this, and here's 1.3 million. And the question is, when was the population 1 million? So here's 1 million. How many years was that? So we can sort of do some calculations in here and take a look at the graph and set one line. If you put this into your calculator, then you can say that this is y1, and the simple way is to do y2 equals 1 million, and then find the intersection of those two lines. You'll be able to solve this and actually do the math on this when we get to the logarithmic equations, the logarithmic section, which is next. And so this time is actually 1985. So 85 years, you'll end up with a t equals your answer here. We'll say x on your calculator, but t in this example, t equals 85. And we have to remember that this is the number of years since 1900. So if t is 85, that means 1900 plus 85 more years, and the year was 1985. There we go.